Today's lecture is going to continue looking at some common distributions. So this is kind of going to be our last lecture where we're just going to review different distributions that are kind of commonly used and look at some of their properties. And again, it's going to give us some nice practice on practicing some of the concepts we looked at before, PMFs, PDFs. And in particular today, we're going to look at expectation, variance, moments, MGFs. So we're going to go back and forth. We're going to look at some discrete distributions, some continuous distributions. The first discrete distribution that we want to look at is called the Poisson distribution, named after a guy with the last name Poisson. I believe it means fish in French, so it's the fish distribution. And the Poisson distribution is a discrete random variable, and it has a support of non-negative integers. So its support is kind of 0, 1, 2, 3, etc. So it's not a finite support, it has an infinite support, but it's a discrete random variable because we have discrete elements of our support. And you can think of the kind of canonical experiment for Poisson random variable, or kind of one of the kind of typical ways that it's used, is to count the number of, let's say, quote, events in some time period. So examples of this Poisson distributions are used to model, say, radioactive decay. So maybe the number of beta particles that are emitted from a radioactive source over a certain time interval might have a Poisson distribution. So say, how many beta particles are emitted in 5 minutes from my plutonium? And you could get no beta particles, 1 beta particle, 2 beta particles, right? And so it's a count. It's a count of the number of events, in this case, radioactive decaying events that happen in time period. And obviously, the probability of 0 is not going to say that I have 1, it's not going to say that I have a million, right? Probably we're not going to have a million decaying events. Maybe we'll have 0, 1, 2, or 3. Maybe those would be more likely. Another thing that it's used to, it's used all over the place in ecological models. For counts, say, of organisms in water, number of fish that I'm capture in my trap, might have a Poisson distribution. It's used in, let's say, microbio. For example, so let's say ecological models, maybe fish capture. Biological models, let's say RNA count. For example, I'm going to count how many pieces of a particular type of RNA I have in a sample, and that's going to have, it's often modeled using a Poisson distribution. So it's a super widely used, very important distribution, and our notation for Poisson, we'd say a random variable x is distributed Poisson, and it has one parameter, and that parameter is lambda. So here, x is the number of events in some time period. That is kind of, we fix the time period in advance, and we say, okay, how many events happen in that time period? And my parameter lambda is the rate of events occurring. So if lambda is high, I would expect more events in my time period. If lambda is small, I would expect less. So when we say x has a Poisson distribution with a rate parameter lambda, what we mean specifically is that the PMF, in this case, little fx, has the following form. It's e to the negative lambda, lambda to the x over x factorial, and this is true over our support. So this is true for x is 0, 1, 2, 3, and so forth. So this is my PMF, right? It's a mass function because it's a discrete random variable. And that's the form of the PMF for a Poisson distribution. We can maybe draw a little graph. It's going to depend, kind of the shape of our PMF obviously is going to depend exactly on our rate parameter lambda, but kind of typically, whoops, let's see if I can count 0, 1, 2, 3, right? Typically, the Poisson distribution looks something like this. It's kind of highest for low values and kind of decays over time. So it doesn't have to look exactly like that, but it kind of decays as we go out. So we have a higher probability, more mass for lower values occurring. Say I have one radioactive decay event rather than 100, which you can have a relatively low number. So that's what the kind of PMF looks like. We could ask, for example, what the expected value of a Poisson distribution is. And that's a calculation that we can do. So the expected value of a Poisson distribution, EX. So I'm going to sum my expected value, of course, for a discrete random variable is just the sum of x times fx, my PMF. And I can sum overall in real numbers, or I can, alternatively just sum over my support. And my support in this case is all numbers 0, 1, 2, 3, etc. out to infinity. So let's plug in to this formula my definition of what the PMF is for a Poisson random variable. It's lambda to the x, e to the negative lambda over x factorial. Now, in order to evaluate what this is, we can use a couple tricks. First of all, when x is 0, the whole thing is 0. So I can actually ignore the case where x is 0. So I could say that this is the sum from 1 to infinity of x lambda to the x e to the negative lambda over x factorial. Right? Because when x is 0, the summand is 0. Notice here I have an x over x factorial, right? So let's just look at this. I have x over x factorial. Of course, x factorial is x. We could write it as x times x minus 1 factorial. And so I can get some cancellation. I could just write this as 1 over x minus 1 factorial. So indeed, I can even more simplify this. I can say this is the sum, goes 1 to infinity. My x over x factorial can be simplified. Just do a 1 over x minus 1 factorial. And I'm going to actually factor out some things, right? So my e to the negative lambda doesn't depend on x. Let's bring that out. And I'm going to factor out, in addition, I'm going to factor out one copy of lambda. So if I pull out one copy, I'll be left with lambda to the x minus 1, right? So it's not a mistake that now I have two things with x minus 1 there. I'm going to change my index here. So I still have e to the negative lambda, one copy of lambda. And instead of summing from 1 to infinity, let's change it so I sum from 0 to infinity. So if I decrease my index by 1, I have to increase x by 1 in my sum. But very nicely, that just leaves me with lambda to the x over x factorial. Now, from Calc 2, hopefully this looks somewhat familiar. So here's a fact to remember from Calc 2. Fact to remember is that if I write, let's say, e to the a can be written as the sum, x goes 0 to infinity, of a to the x over x factorial. So actually what I have going on here in my sum is this whole sum here. It's going to be like e to the lambda, right? Because instead of a, I have lambda. So what I'll be left with is e to the negative lambda, one copy of lambda, and then this sum, this is the power series of, or the Taylor series of e to the lambda. So this is just e to the lambda. And of course, so I guess there's an equal sign here. Of course, my e to the lambda, e to the negative lambda cancel, and I'm just left over with lambda. And what we're calculating the expected value, right? So let's put that in a box. What we have just shown is that the expected value of a Poisson random variable with rate parameter lambda, its expected value is lambda. So this parameter lambda is basically kind of average or / expected number of events in one time period. So I said x is kind of the number of events that occur in some time period. Lambda is basically on average in that length of time, how many events do we expect to have happen? So that's one way of interpreting lambda. Okay, so we used a couple tricks when we calculate the expected value. One of these tricks is that we canceled x and x factorial in a nice way. And that helped us out because then we could just write this as a geometric series or a power series of e the whatever. So let's kind of look at this trick again. We can play this trick. This is a trick you can play with Poisson random variables. Instead of looking at e to the e of x, let's look at x times x minus 1, right? Looks a bit scary, but our law of the unconscious statistician says that I can write this as just x times x minus 1 times fx, or indeed, let's write this out, it's x by x minus 1, and what's my PMF? E to the negative lambda, lambda to the x over x factorial. And I'm going to play a similar game. I'm going to group, well, actually, let's hold up here. First thing we want to do is note that when x is 0 or 1, so when x is 0, the whole expression is, and the summand, as it were, is 0. When x is 1, x minus 1 is 0, the whole thing is 0 also. So actually, I can restart my sum at x is 2. Because when x is 0 and x is 1, the whole thing is just 0. Okay. Now, let's group these things together. Let's look at this thing, which is x times x minus 1 over, x factorial. So this is x by x minus 1. And at the bottom we have x factorial, which you can write as x times x minus 1 times x minus 2 factorial. And so we could cancel some of these things out, and this would just be 1 over x minus 2 factorial. So this should feel pretty similar to what we did previously. We're just playing some games, so let's continue on down to the next line. Let's do this. Let's leave some space out front. So let's say x goes 2 to infinity. X minus 1, x times x minus 1 over x factorial. We just said I can write that as 1 over x minus 2 factorial. And let's factor out 2 copies of lambda. So we'll be left with lambda to the x minus 2. And let's factor out e to the lambda. Okay, so if we do this, then we should be able to play the kind of same trick we played last time, where we factor out, or where we re-index it, and it becomes a geometric series and works out nicely. So we have lambda squared, e to the negative lambda. Let's decrease our index by 2, which means we increase it by 2 in the summand. So we get an x factorial in the basement, lambda to the x. And this whole thing here, of course, is just e to the lambda, because that's the Taylor series of e to the lambda. And so we're left with lambda squared e to the negative lambda e to the lambda, which gives us just lambda squared. So what did we show in this case? What we showed in this case is that the expected value of x by x minus 1 is lambda squared. Okay. And you can imagine you could play this game with x by x minus 1 by x minus 2, right? You would get, what, probably lambda cubed, for example. We don't need to do it. In this case, of course, we can expand out this as x squared minus x. So those are equal. And of course, I could distribute my expected value over a minus sign. So e of x squared minus e of x. And we said e of x is lambda. And all together, we said this whole thing was lambda squared. So some algebra says that the expected value of x squared better be lambda squared plus lambda. Seems right. And of course, why do we care about the expected value of x squared? We can look at the variance. Now we can use our shortcut formula. I could say the variance of x is the expected value of square minus the square of the expected value. This is lambda squared plus lambda minus lambda squared, which just gives us lambda. So interestingly, the variance is also lambda. So we said the mean is lambda, and the variance of a Poisson random variable is also lambda. So that's almost kind of a characterizing definition of what it means to be a Poisson random variable. Its mean and its variance are the same thing. It's kind of a rare occurrence, but it's true, and it's a fact that is super useful and exploited all the time for when modeling things with Poisson random variables. So more generally, we could look at, say, the MGF for a Poisson random variable. So recall that our MGF, m of t, is the expected value of e to the tx, which is, in this case, sum over our support, 0 to infinity, e to the tx, fx, right? And sum goes 0 to infinity, e to the tx, and let's plug in what our MGF is. It's e to the negative lambda, lambda to the x, over x factorial. And let's see again, well, what doesn't depend on x? Let's pull this e to the negative lambda, right? Doesn't depend on x. And what are we left with when we do that? We get the sum, which goes 0 to infinity, of, I'm going to write it this way. I'm going to say, I'm going to write it like this, lambda e to the t to the x over x factorial, right? That's allowed. If I distribute my x through, I get lambda to the x e to the tx. And this, again, is basically a, and so it's basically sum of a to the x over x factorial from 0 to infinity, and we know that it's e to the a. In this case, a is lambda e to the lambda t, so this all becomes, we still have our e to the lambda, or e to the negative lambda, and then we get another e to the lambda e to the t. And that is the MGF. You could simplify it, so you could say, so here I say exp, that's exponential, so it's e to the x, right? Or e to whatever the argument is. I can factor this as lambda e to the t minus 1. That's typically how you'll see it written, right? So here, my notation, exp of, say, a is just e to the a. It just allows me to write exponentials on one line. This is kind of typically how you see it written, but either way is correct. Okay. So that's Poisson. Let's stop there with Poisson random variables. They don't have a nice kind of closed form CDF, so we're not going to look at that. And let's move on to a continuous distribution. And let's move on to what's called the gamma distribution. And the gamma distribution is going to generalize the exponential distribution. And let's first talk about why it's called the gamma distribution. So let's talk about what is called the gamma function. And I'm going to give you some facts about this function called the gamma function. I'm not going to prove anything. Don't quite have the time to do that, but let's talk about some facts. So what is the gamma function? The gamma function is going to give its name to the gamma distribution. So I'm going to make a plot of x versus x factorial here. So if I plot x by x factorial, so I have 0, I would have 1, I would have 2, 3, go 4, something like that, right? 0 factorial is 1, 1 factorial is 1, 2 factorial is 2, 3 factorial is 6, 4 factorial is, this is obviously not the scale, but point being it's going to be 24, which is going to be way, way, way up here, right? My scale is not quite correct. 4 factorial would be way up here. So if you plot factorial, obviously it's this really fast increasing function. And factorial is only defined for integers, right? We don't really have a definition of what is 1/2 factorial, what is 2.2 factorial, right? It's only defined for integers. And what the gamma function does is it's going to extend factorial to, in this case, positive real numbers. So the gamma, it's supposed to be 2 n's, gamma function, it is going to extend x factorial to positive real numbers. And so it's going to have any integer, it's going to be equal to x. It's going to kind of pass through in some way the x factorial, but it's going to have defined values. You could imagine kind of interpolating these points, right? So you get some function that looks something like that, right? It's going to go through our values here and our x factorial values here. So in some way it's going to kind of pass through all those values. So let's look at how it's actually defined. The gamma function, so gamma, it's a capital gamma, is a function that takes in, say, a positive real number, and it's going to spit out another positive real number. And the function is defined as gamma of a. It's kind of a wonky definition. It's the integral from 0 to infinity of x to the a minus 1 e to the negative x dx. So that's an integral that you can calculate. And I'm going to claim that it kind of does something like what I'm doing here, where it's kind of interpolating through these x factorial values. The important fact to know is that if a is an integer, right? So in this definition here, a can be any positive real number. And this integral is well defined. However, if a is an integer, we have a special case, right? Gamma of a is going to be, well, we'd kind of like it to be a factorial, but it's not quite going to be. It's actually kind of offset by 1. A minus 1 factorial. Equivalently, you could think about this as gamma of a plus 1 is a factorial. So it does kind of pass through these factorial numbers, but it's kind of as offset by 1. So, for example, gamma of 1 is 0 factorial is 1. Gamma of 2 is 1 factorial is 1. Gamma of 3 is 2 factorial is 2. Gamma of 4, 3 factorial, 6, etc. All right. So it does actually give us back the factorials, but it's kind of offset by 1. A further fact that's really useful is that, so let's just say this is kind of fact 1 that's very useful. A further fact of this gamma function is that, notice that for factorials, like I could write x factorial as x by x minus 1 factorial. We did this in the previous problem with the Poisson random variable, right? And for gamma, it is kind of similarly true. So this is true for x integers. But for gamma, you could always write gamma of, let's say, a plus 1, gamma of a plus 1 is a times gamma of a. So it's kind of a similar kind of statement, right? Notice that gamma of a plus 1 is a factorial, if a is an integer, would be a times gamma of a would be a minus 1 factorial, right? So that's definitely true for integer. But this is kind of more generally true. For any real number, be an integer or not, gamma of a plus 1 is a times gamma of a. I guess the other way you could write this as is gamma of a is a minus 1 times gamma of a minus 1. Either way is fine to think about this. But it's a similar kind of property where I can like recursively write my gamma function the same way I can recursively define factorial. A factorial is a by a minus 1 factorial, or gamma of a is a minus 1 times gamma of a minus 1, right? You have to remember it's going to offset by 1. So just to summarize, my important facts for this gamma function, right? This gamma function is quite a useful function. Is that 1, gamma of x plus 1 is x factorial for x an integer, and 2 is that gamma of x plus 1 is x by gamma of x. So these are the facts I would memorize. But the kind of general feel of the function is that it's trying to act like the factorial function, but allow us to plug in any positive real number. Okay, so this is kind of a sidebar, but it's going to be really useful, and it's going to explain why the gamma distribution is called the gamma distribution. So let's talk about the gamma distribution now. Gamma distribution. And I claim that it generalizes the exponential. And so we say that x is distributed with a gamma distribution, and there are two parameters. We're going to call them A and lambda in this case. The parameters are not the most easy thing to interpret. You could think of them as shape and rate is maybe one way to think of them. Not the easiest thing to interpret. What we mean when we say X has a gamma distribution, so kind of definitionally, is that the PDF has the following form. It's lambda e to the negative lambda x. Now, if I stopped there, there's more to come, but if I had stopped there, that is a exponential distribution, pretty much. But it's not quite that. We're going to add on a lambda x to the a minus 1, and then we're going to divide through by gamma of a. And this is the PDF. It has a support of positive numbers. Okay. So this is the PDF. And it generalizes the exponential distribution. If we notice that when a is 1, fx is lambda e to the negative lambda x. It's lambda x to the 0 over gamma of 1, which, of course, is just lambda e to the negative lambda x. Because x, whatever 0 is 1, and 0 factorial, gamma of 1 is 0 factorial is 1 also. So when a is equal to 1, this is just the exponential distribution. But when a is not equal to 1, we get something richer than the exponential distribution. And let's look. So all the facts we derive should be true. That it should be true that when a is 1, we get exactly back our exponential distribution. But the gamma distribution allows us to have kind of more interesting shapes. So if I look at, say, the PDF, you could get something that looks like this. Or if I change my shape parameter, I could maybe get something that looks like that. It's not quite a bell shape, but it's kind of like maybe something like that, right? So this is x is 0. It's only has positive density for positive numbers. But I can play with different shapes, but it kind of has this, it's a very kind of flexible distribution on all positive numbers. Okay. So let's look at some properties, and keep in mind when a is 1, these properties better reduce to what we know is true of the exponential distribution. So for example, if we look at expected value, we knew something about expected value for exponential distribution, but what about this gamma distribution? Expected value of x, right? So it's the integral x fx dx, and I can integrate over my support, let's say. So let's plug in integral 0 to infinity of x, and what's my PDF? Lambda e to the negative lambda x, lambda x to the a minus 1, all over gamma of a, and we get a dx in there. So this is an integral, and if I told you a, and I told you lambda, potentially you could solve it. You might have to do integration by parts a lot of times. I'm lazy and I don't want to do integration by parts that many times. So what we're going to do is we're going to employ some tricks so I don't have to solve any integrals, because I don't really like doing that. So let's, first of all, I'm going to factor out, so let me just back up. The general trick is what I'm going to try to do. Let's just write trick. So I'm going to try and write it by some constant times the integral of the PDF of some other gamma. And then I'm going to say, aha, this integral of the PDF of the gamma should be 1, And so my expected value will just be whatever my constant is out front. Okay, so we've seen that trick before. It's exploiting the fact that the integral of any kind of PDF is always going to be 1. So if I can factor things out and rearrange it and pull some smooth tricks here, I can make the integral just go away and I don't actually have to solve the integration problem. Okay. So in this case, in particular, I'm going to make it the PDF of a gamma. Instead of a gamma lambda a, it's going to be a gamma lambda a plus 1. Right? So if you recall, our distribution was gamma a lambda. And I'm going to, whoops, probably get those parameters in the right order. Let's say a plus 1 lambda. Okay. All right. So, how are we going to do this? We're basically just going to factor some things out until I get what I want. So I'm going to try and turn this thing into, from a gamma a lambda to a gamma a plus 1 lambda. So let's first factor out, first thing I'm going to do, I'm going to combine this x here with this x here, right? I'm going to shove that in there. So I could rewrite this as the integral of lambda e to the negative lambda x. And then instead of lambda x to the a minus 1, I'm going to say it's lambda x to the a. So I can shove that in there. But now I have too many lambdas, so I have to take out 1 there. Now this is true. Okay. So I'm just rearranging. I just pull that 1 lambda and I combine things. And my next trick here, equal sign there, is I'm going to pull out that gamma of a. So let's say 1 over lambda gamma of a, lambda e to the negative lambda x, and I'm going to say it's a lambda x of a plus 1 minus 1. All right, that's allowable. Ultimately, what I want is I want this PDF of a gamma a plus 1 lambda, right? So the PDF of a gamma a plus 1 lambda should be lambda e to the negative lambda x to the a plus 1 minus 1 over gamma of a plus 1. That would be the PDF of a gamma a plus 1 lambda. And I almost have that here. But what I need in my denominator now is I need to have this gamma of a plus 1. So I can put that there, and then I could also put another one on top, pull it out, it doesn't depend on x. That's allowable. Now I have exactly made my PDF. So this is a gamma a plus 1 lambda, integrates to 1. So I've turned my expected value problem into just the integral of a PDF. Integral of a PDF is easy, it's always 1, right? Now I actually have to solve the complicated integral. So that thing's always going to be 1, which means what I'll be left with is gamma of a plus 1 over lambda gamma of a. So you could leave it there. I suppose that's technically true. But I can use some facts I know, which is that gamma of a plus 1 is a times gamma of a. All right, so this is a fact I know. I said this is one of our 2 important facts. And so this I could write as a gamma of a over lambda gamma of a. And obviously my gamma of a's, which is just some number there, cancels. And I get a over lambda. So that is my expected value. And really cleverly there, I didn't have to solve any integration problems. Okay, so that's a really clever trick. And it turns out this trick is more general, and I can use it to get any moment of a gamma distribution. This makes this distribution really nice once you see this trick. So I had done this trick where I looked at the expected value of x, but what if I look at the expected value of x to the r? So I look at the rth moment. I'm going to real quick do the same trick, right? I'm going to move a little fast because we've seen this before. But now it's the integral of x to the r times my PDF, lambda e to the negative lambda x to the a minus 1 dx, and in the basement here I have a gamma of a, right? Okay, that's the integral. Technically, you'd have to solve. I don't want to solve it, all right? So what am I going to do here? I'm going to factor out my gamma of a. It doesn't depend on x. And so I'll put 1 over gamma of a. I'll have an integral. I'm going to push my x into, I'm going to push this x, combine it with that x, right? So what I'd like to say is this is lambda e to the negative lambda x times lambda x to the a plus r minus 1. But now I have too many lambdas because I've just arbitrarily increased this, so I have to divide through by lambda to the r. Now I'm okay. Now these two statements are equivalent. And this almost is the PDF. What I want to make this is the PDF of, instead of a, before we had gamma of a plus 1, now we're going to have it as a gamma of a plus r. In order to make it PDF of gamma of a plus r, I need in my basement a gamma of a plus r. Now that is really that PDF, but of course I need to multiply by a plus r on the top here, just to cancel it out. And now, as I said, this PDF integrates to 1 because it is exactly the PDF of a gamma a plus r lambda. Just look at the formula. That would be the formula for that PDF. That thing integrates to 1, and Bob's your uncle. I get that expected value of x of r is just whatever I have out front, which is gamma of a plus r, or gamma of a lambda to the r. Now, in general, this is kind of as simple as we can get it. And that gives you a formula. You give me a, you give me r, you give me lambda, I can calculate it. And so we saw before that if r is 1, so r is 1, then this thing became a over lambda. Notice if a is 1, therefore we get 1 over lambda, which is the expected value of an exponential random variable, right? So as I said, when a is 1, we get back what we expect for an exponential random variable. But we could also say, we could do this, give me another r, let's say r is 2, I could say, well, what's the expected value of x squared, the second moment? And here's my formula. It's gamma of a plus 2 over gamma of a, and there's a lambda squared in the bottom there. And we can then twice apply our rule about the gamma function. Gamma of a plus 2 is gamma of a plus, is a plus 1, gamma of a plus 1 over gamma of a lambda squared. And then let's apply it one more time. A plus 1, gamma of a plus 1 is a gamma of a. Got a gamma of a in the basement, a lambda squared in the basement. And now my gammas go away. And what I'm left with is, well, let's say it's a squared plus a over lambda squared. So this is the second moment. This is the expected value of x squared in this case. Well, that's nice. What this allows me to do is I could, of course, calculate the variance of x. This would be by my shortcut formula, e of x squared minus the expected value of x quantity squared. Second moment here we said is a squared plus a over lambda squared minus, and our first moment there was a over lambda quantity squared. What do we get? A over lambda squared. And so the variance is a over lambda squared. And when a is equal to 1, that's kind of a sidebar, we get 1 over lambda squared, i.e. variance of an exponential distribution. As we claimed, when a is 1, the gamma distribution just reverts to an exponential distribution. Cool. That's real nice. Okay. So we want to kind of do 2 more distributions today. So that's a continuous one. So let's go back and look at another discrete distribution. Do some more practice of looking at moments, for example. And the distribution that we're going to look at is called the geometric distribution. And the reason it's called the geometric distribution is because it is going to have to use the kind of geometric series over and over and over again. And this is a random variable we've seen. We've actually kind of worked with this one before. So if I have the kind of, let's say this is the canonical experiment. So if let's say if I flip coins independently, and let's say each has a probability p, which is some number in 0 to 1, of a heads, of getting a heads. Let W be the waiting time until I get a heads. So if I flip the coin the first time, let me just write a table here. Outcome and what W is. If I flip the coin the first time and I get a heads, then my waiting time is, or my number of flips I need to make is 1. If I get a tails first and then a heads, it would take me 2. If I get a tails, tails, heads, that would be 3, and so forth. If this is the case, if W follows this experiment, then W, our waiting time, is said to have a geometric distribution with a parameter P, defining the probability of success. So the support of this random variable is just the positive integers, 1, 2, 3, whoops, what comes after 3, 4, etc. Right? So it's kind of this waiting time thing where I say if 1 heads, they're going to wait once or twice, 2 flips, 3 flips, 4 flips, and I'm going to say how many flips do I have to wait before, the W for wait, how many times do I have to wait before I get a heads? And the PMF, right, so this is a discrete random variable, so it has a mass function of PMF, is Fx is, well, if I have to wait X times, so I have to make X flips to get my first heads. So maybe I should say to get the first heads. If I have to make X flips to get the first heads, what does that mean? It means that I had X minus 1 tails, and if they're all independent, I have a 1 minus P probability to get tails, and they're independent, so I can say that's 1 minus P to the X minus 1. So if X minus 1 tails in a row, tails, 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 right? And then I finally get my heads, P. And so this is the PMF, and this is obviously for the support, which is 1, 2, 3, etc. So it's a pretty simple PDF, or PMF. Tails, 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 X minus 1 times. So the probability of getting tails X minus 1 times in a row by independent flips is 1 minus P to the X minus 1. And then I have to get my last one, has to be a heads. If it took me exactly X flips to get my first one, so I gotta have an extra P in there. So that is my PMF. Okay. This random variable actually, unlike some things like the gamma distribution, has a nice CDF form we can derive. So the CDF, Fx, is the probability that my waiting time, in this case, is less than or equal to X flips. And I know I can just say that this is the sum, I goes 1 to X, of my PMF, Fi. All right, so think back to when we introduced CDFs, that's kind of the fundamental for discrete random variables relation between CDFs and PMFs. So I can just sum up my PMF over all values less than or equal to little x. And our formula for that is sum I goes 1 to x, p, 1 minus p to the I. And this just recalls, just actually, derive a closed form for this. It involves remembering that, say, from Calc 2, that, again, we see in this fact, if I sum I goes 0 to n minus 1 of r to the I, this is 1 minus r to the n over 1 minus r. So this is kind of the partial sum for a geometric series. And that's pretty much what we have here. We've got to rewrite it because our index currently isn't in the right form. So first of all, let's factor in a p, and then let's re-index this starting at 0. So let's say it goes 0 to x minus 1, in which case it'll be 1 minus p to the I minus 1. Ooh, I really don't want I minus 1 in there, right? So how about this? How about I divide by 1 minus p and make that I? Does that seem right? Oh, you know what? We don't need to do that. You know why? Because I wrote the PDF wrong, the PMF wrong. This should be an I minus 1. I'm sure someone's screaming at their computer, right? To the minus 1, 1 minus p to the x minus 1, or 1 minus p to the I minus 1. Okay, so now when I re-index, I get the right thing. Little hiccup there, okay. Moving on, so we got a p on the outside, and now this just follows our formula. 1 minus r to the n, so it's 1 minus 1 minus p to the n, which is x minus, or n minus 1. It's x minus 1, so n is x. And at the bottom, I just get 1 minus, it's supposed to be 1 minus p. 1 minus 1 minus p is p, so actually, it all really simplifies here, because p and 1 minus p is just p. So our CDF has a nice closed form. This is our CDF fx. It's just 1 minus p to the x. And basically that's just writing out the form of it and using this Calc 2 fact. It's real nice. We can try and get, let's say, what do we want to look at? We could say get the expected value. So let's look at and see if we can get the expected value for a geometric random variable. This is a really fun trick to do this. The expected value of our geometric random variable is the sum, of course, by the formula, it's just the sum 1 to infinity, that's our support, of, let's say, I, instead of x, we're using I. And then our PMF is p times 1 minus p to the I minus 1. And let's factor out that p, because we can, doesn't depend on I. I goes 1 to infinity of I times 1 minus p to I minus 1. Okay. So here's the trick. What we're going to do is we're going to recognize that if I look at, say, I, 1 minus p to the I minus 1, this is negative of ddp of 1 minus p to the I. What? Okay, take a minute to absorb that. Work from right to left here, go backwards. If I were to take the derivative of 1 minus p to the I with respect to p, I would bring down my I here. I would have 1 minus p, I'd lower the power to the I minus 1, and then I'd take a derivative of the inner, and the derivative of the inner would just be negative 1. So we get a negative sign there. So this is exactly true. This is my summand here, right? So this thing boy. Way back up to the top there. What's going on? Okay. Come on. Okay. So we have this derivative relationship. This is my summand here, right? That's that summand. So what I'm saying is that I could rewrite this thing as p times the sum, I goes 1 to infinity, of d dp, and we probably should just throw a negative sign out front, of 1 minus p to the I. Where does that get me? What it does is that if I'm allowed to interchange my summation and my differentiation, and you have to think back to Calc 2 under what circumstances I'm allowed to do that. And in this case, it's a well-defined function, so I'm allowed to do this. If I can interchange those, I'm just going to switch I'm going to say, well, I'm going to pull out my ddp, and then this is the sum, I goes 1 to infinity, of 1 minus p to the I. And now, if we say r is 1 minus p, this thing here is just basically a geometric series. Not quite. It's 1 to infinity of r to the I. So it's almost like a geometric series. What we have to do to make it properly a geometric series is, you'd say it's negative p, ddp, it needs to start at 0. So this should be, we'll lower my index by 1. So say this is the sum from 0. And got to make sure my differentiation operator is in the right place. Let's write it like this. I want my sum to go from 0. But I want my index to be I. So I'm going to have to pull out a 1 minus p. Now that should be correct. Because you could write it as, if you push that 1 minus p in, it would be 1 minus p to the I plus 1 at 0. That would be 1, which is what it was in this upper one here. Okay, so I claim that those are equal. That's believable. And now this really is the geometric series, 0 to infinity r to the I, and we have a nice formula for that, right? So let's write down what we have. Negative ddp, negative p times ddp of this expression is 1 minus p, and this thing, of course, is 1 over 1 minus r. The geometric random variable, because we're going to exploit various properties of a geometric series to derive quantities, hence the name. So 1 over 1 minus r is 1 over 1 minus p. Of course, 1 minus p, this is just 1 over p. So what I get, negative some derivative 1 minus p over p. And you could do some calculus. If you do the calculus on this, oops, I forgot my p here, so negative p, take the derivative, I'm going to get negative 1 over p squared. You can believe that. Do the little calc problem, calc 1 problem, and that, of course, negatives cancel. I just get 1 over p at the end of the day. And this, of course, was our expression that we were deriving for expected value. So that derivative trick is a really useful trick to know for sums. And when you can interchange them, which you can in cases like this, it makes that sum kind of tractable. So our expected value is just 1 over p. So that makes sense. If I have, if my probability of heads was 1 over 100, I would expect to wait about 100 flips in order to get my first heads. If my coin is fair and the probability of p of getting heads is 1/2, I would expect to have to make 2 coin flips to get my first heads, on average. All right, what else can we do? Of course, we can look at, for the geometric random variable, we could look at the MGF. So let's look at the MGF. What is the moment generating function? It's a function of some real number t. M of t is the expected value of e to the tx. Okay, In this case, that's the sum. My support goes, let's use I. We've been using I, right? I goes 1 to infinity. E to the t, in this case, it's I. And then my PMF is P, 1 minus P, I minus 1. Okay. Let's factor some things out of the sum. First of all, this P doesn't depend on I. Let's factor it out. And I'm going to factor out one of these e to the t's. And it's going to be obvious why I want to do that in a second. That will leave me with I minus 1 e to the t's. And then, whoops, I factored out that p. I'll be left with a 1 minus p, the I minus 1. So now I have a bunch of I minus 1s. My sum starts at 1. So I could re-index my sum, start at 0. I decrease my index by 1. I have to increase it in the sigma. I have to increase it by 1 in the summand. E to ti, 1 minus p to the I. And now let's just group things, and we'll see, not surprisingly, this is going to give me another geometric series, right? So sum I goes 0 to infinity, e to the t times 1 minus p, all of that to the I. Just group things differently. And this is a bigeometric series, right? That's going to allow me to say, of course, I have p e to the t on the outside, and then geometric series says this is 1 over 1 minus r. In this case, my r is basically that. And so I will have 1 minus e to the t times 1 minus p. So that should give me my MGF. And you could use this MGF, right? So that's actually a really useful thing to derive in this case, because, for example, if I wanted to calculate the expected value of w squared, I guess I use w in this case instead of x, right? This should be a w. Doesn't really matter. If I wanted to say calculate the expected value of w squared now, you could actually play a similar trick to this one, but then you have to deal with the second derivative, and it's going to start to get really messy. But alternatively, what I could say is if I wanted to calculate the second moment, e of x squared, maybe I want to calculate the variance, what I could do is I could take two derivatives of this thing, and it's not too bad, take derivatives with respect to t, and I evaluate at t is 0. If I did that in this case, what I would get is that, for example, I'm not going to do the calc problem for you, but you can do this calculus problem. Maybe pause it and prove to yourself that you get 2 minus p over p squared. And so that's the expected value of x squared, and that's a much simpler way of getting it. It's taking derivative of this thing. Not the nicest thing in the world, but not bad. You can do it. Rather than trying to figure out some weird second derivative trick with summations. And this allows me to say the variance, which of course is the second moment, minus the first quantity squared. This would be 2 minus p over p squared minus, my first moment was 1 over p, my mean was 1 over p, square that. And a little bit of algebra will get you to our formula for our variance, which is 1 minus p over p squared. So that's the geometric distribution, so named because basically every property you try to derive from it, you're going to end up exploiting the geometric series, either partial series or the full thing. And it's basically the waiting time for a certain event to happen. In this case, I had defined it as a coin flip, right? But it's any series of independent events. If I do an event over and over and over again, it has some probability of coming heads. And I keep doing it until I get kind of a success. Any kind of binary experiment I do, you can write as a geometric. So it's a waiting time distribution of waiting times in a discrete sense. Okay. So the last distribution I think we should look at today, and the last one we will look at before move on to our next topics of random variable transformations is the beta distribution. So this is going to be our last distribution. And this is going to be a continuous random variable. So we did a discrete one, now let's do a continuous one. And the beta distribution is kind of related to the gamma distribution in some ways. There's something called the beta function. And the beta function is a function of two real numbers. So A and B, let's say, are positive real numbers. Beta of AB is the integral over 0 to 1 of x to the a minus 1, 1 minus x to the b minus 1. Okay, so that's one way of defining the beta function. Nobody actually does that. Really, the fact to know is that the beta function is related to the gamma function in the following way. Beta of AB is gamma of A, gamma of B, over gamma of A plus B. So this is the more important fact to remember. And then, typically if A and B are integers, you can relate this to certain factorials. So that's the beta function. The beta distribution is basically going to look very similar. It is a continuous random variable. So we say maybe x is distributed as beta, has two parameters, a and b. And if I say x is distributed with a beta distribution with parameters a and b, this means that my PDF, continuous random variable, the PDF takes the following form. X to the a minus 1, 1 minus x to the b minus 1 over beta of AB. And this is a random variable over the unit interval, over x between 0 and 1. So if you were to plot, say, you could look at different plots of the PDF, fx against x, and it's only going to have a positive density between 0 and 1. And depending on A and B, it's going to have different shapes. So maybe it looks like this. Another possibility is it looks like this. It could maybe look like this. There's many different shapes you can get. So it's basically a rich family of distributions where we're constraining the random variable to live in 0 to 1. And you can get many different kind of shapes depending on the different parameters for A and B. And A and B are kind of generally pretty hard to interpret. So the beta distribution is in some ways kind of cousins with the gamma distribution. Gamma distribution is positive numbers, beta is between 0 and 1. And there's some other kind of more subtle relationships between them. So let's look at things. So this is our PDF, right? And of course, one property, we could say what's the average value, what's the expected value of this distribution? Of course, I can integrate over my support of x fx dx, which in this case is x, and my PDF is x to the a minus 1, 1 minus x to the b minus 1, and I have a beta ab in the basement, of course, with respect to dx. Okay. We're going to play the same trick we did as in the gamma. I don't want to solve this integral. It's an awful integral. It looks horrendous. Let's convert it into something related to the integral of a beta distribution, and then the integral just goes away. Integrates to 1, don't have to deal with it. All right, so this trick is this. It's so-called the PDF trick, I think, or the PMF trick. People, statisticians don't like solving integrals, and so we came up with all these tricks so we don't have to solve these integrals. So, and it works for some random variables, others it doesn't, but gamma and beta are kind of two classic examples where you can simplify all the calculations. Okay, so we want to make it look like let's say make integral. What I want to do is I'm going to make it some constant times the integral of a beta, and I'm going to, instead of AB, it's going to be A plus 1B. And then, of course, what I'll say is, aha, I'm integrating a beta PDF of this beta thing, and the integral is going to be 1, and my constant up front will be my expected value. Okay, so the same trick we played over and over and over again. So I want to make it look like a beta A plus 1B, right? So the beta A plus 1B, so the PDF of a beta A plus 1B would be have the following form. Let's just write it out. It would be x to the A plus 1 minus 1, 1 minus x, the B minus 1 over beta of A plus 1 B. Okay, so this is what I want to achieve. I want to get that form out of this form. Okay, well, let's look at it. So I have an integral, 0 to 1. X to the A, I can combine these x's here, right? This x and this x, I can combine them as x to the, well, let's write it in a dumb way, but x to the A plus 1 minus 1. It's x to the A, right? But I want it in this form. I want x to the A plus 1 minus 1, so I recognize it as the PDF of a beta. I get a 1 minus x to the B minus 1. Still have my dx. Now in the basement here, what I really want here, of course, is I want, if I were to have a beta of A plus 1B in the basement, that beta function in the basement, then it would be exactly this PDF. So I could do that, but I have to multiply on the outside by the corresponding thing, and of course I have to factor this out too. So it's a little cramped there, but I've just multiplied, I have that in the top and the bottom, so they cancel, and I have my beta of A plus B in the bottom. So this thing obviously is the PDF of a beta A plus 1B, integrates to 1, and so overall I get beta of A plus 1B over beta of AB. And so you could stop there. That is technically the expected value of x, but that's no fun. Let's expand this out, right? So my definition, I'm going to expand this out using the definition of the beta function. So beta of AB is gamma A, gamma B, gamma A plus B. And then on top I have gamma A plus 1, gamma B over gamma of A plus B plus 1. So things will cancel. There's gamma B's will cancel. And gamma of A plus 1 I can write as what? I can write as A times gamma of A. And gamma of A plus B plus 1 I can write as A plus B times gamma of A plus B. All right, I can reduce each of them by 1. And then I have in the basement, I still have a gamma A over gamma of A plus B. Now I get lots of cancellations. Cancel, 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 cancel. Lo and behold, that is my expected value. So that actually works out quite nicely. It's a really nice simple formula. It's just A plus B, A over A plus B. So that is, of course, my expected value. Cool. Now, the next thing we typically want the variance, and to get the variance, we typically will calculate the second moment. But like the gamma distribution, we can actually play this trick for any moment. So we can easily derive a formula for any moment of the beta distribution. So E of x to the r, I'm going to run through this real quick, okay? Integral is 0 to 1, x to the r times the PDF of the beta, x to the A minus 1, 1 minus x to the B minus 1, divided through by beta function of AB dx. Okay, let's factor out that beta function in the basement. Combine the x's, x to the a plus r minus 1, 1 minus x to the b minus 1 dx. And if I want to make this a beta, the PDF of a certain beta, I want to make it the PDF of beta a plus r b. So I could do that by dividing by beta function of a plus r b and multiplying by that same quantity. If I do that, so this is exactly the same trick. Now I have an arbitrary addition r. This is the PDF of a beta random variable, and therefore integrates to 1. And so my moments, my rth moment of a beta random variable is beta of a plus r b over beta of ab. And that, I think, is, in general, for an arbitrary r, is as simple as you're going to be able to make it. If we want to calculate the variance, we could say, well, if r is 2, this would be beta, this is going to be beta of a plus 2b over beta of ab. And we can play the same simplifying games. So you can play the same simplifying games, right? This is gamma of a plus 2, gamma of b, or gamma of a plus b plus 2, over gamma of a, gamma of b, gamma of a plus b. And I'm going to make a claim that gamma of a plus 2 is a plus 1, gamma of a plus 1, which is a plus 1 times a, gamma of a. And similarly, gamma of a plus b plus 2 is gamma of a plus b plus 2 is gamma is a plus b plus 1 times gamma of a plus b plus 1, which is a plus b plus 1 times a plus b gamma of a plus b. And so when I cancel things, gamma of b cancels, gamma of a cancels with that gamma of a plus b cancels that, gamma of a plus b. What we're going to get is, in the top here, we will be left with a times a plus 1, and in the bottom, we'll be left with an a plus b times a plus b plus 1. I went through that a little bit quickly, but you can go through it slower. But just some simplifying tricks with the gamma function. So this, of course, is my second moment, right? And so the variance of x by my shortcut formula, e of x squared minus e of x quantity squared. And we now know what the second moment is. We know what the first moment is. There's some algebra. You can show it has the following form: ab over a plus b plus 1 over a plus b squared. And that's my variance. So there's a formula for variance. If you look up the formula for variance of a beta random variable, that's what you get, and that's how you get it. Not the most interpretable thing in the world, but it is what it is. That's the variance there. Okay. So we've done a real, kind of tour de force here of a couple different types of random variables. Mostly to practice different calculations of and see how you can calculate expectation, CDF, PDF, PMF, moments, moment generating functions, etc. Gives you practice. I don't expect you to know all these tricks or memorize any of these tricks. It's good to see for these common distributions to have kind of a pantheon of different common distributions that you kind of know about, have some feeling for what they are, and it's good to see once in your life how some of these properties are derived. So we're going to stop there, and next time we'll talk about transformations of random variables.